Hello, Robin. Please uh, switch on the voice button so that we can hear you. Bu hoparlörü nereye takıyorsun? Bir tahmin ediyorum ama hoparlörü nereye takıyorsun? Yani yanlış yere takmayın. Ben takmadım hiç. Şurası değil mi? Bir bak da
Orada zaten başka yok.
göremiyorum. Şurası başka yok.
Şurada. Şeye yakın.
Şeyi de şunu da açmamız lazım. Kumanda var mı?
Ha, kumanda şeyliydi ya. Benim odada vardı galiba. Ben getireyim hocam.
I cannot hear, Robin. You should click on the button.
Can you hear now? Can you hear?
I can hear you.
Yeah, I can, and then, yeah, so will you just wait here now, is it? Hold it. So how does he put up his paper?
Just let me assign you as a moderator.
Yeah, the moderator, yeah.
Yeah.
You're a professor now. Okay, you're not now. He's a moderator now. Is that okay? No.
Can you send me the full presentation file?
Yeah, can you send the presentation, Robin, to him? Full. Can you send the full presentation?
I had, yeah. If I can, I have.
You wanted to send the presentation?
To get out of this to click on it.
You had sent one you had sent. Is it okay?
He has it. It's okay.
Oh, he has it.
You have it now, Hussein, yes?
Let me.
So you will put it up when Robin is starting to talk, yeah?
Burada ekranda.
Okay.
Let me find you.
You have it now.
Just a moment.
Is this charger? I have it.
It is because it was on all night,
It still have
plugged in.
it on charger.
Maillerden bulalım.
What's happening there, Robin? What did I hear there?
I don't know what you did there. No, it's all well charged up. Okay.
I don't know how to do it. No internet here, actually. There's no internet, Robin. Do you find that?
Well, I'm on as far as I know. I don't know about out there. It's your little. Hello. Sharing audio.
Just a moment.
I can hear you. Can you hear me?
Yes, I can hear you.
Can you hear me?
Yes, I can. I hear you. I can hear
And I
you.
see something. Oh, I hear my. Here, I see my presentation. I believe.
Just a moment. Müsaadenizle.
Oh dear.
Is your presentation same as you sent to me?
Hello. No, can you come here a minute?
What did you say, Hussein?
He can hear me.
Can you
Here
hear
is my presentation, but it's very small.
What do you want? What do we do now, Hussein? Ne yapacaksın?
Robin, is that the file you like to present?
That's what he's presenting. Yeah, he hasn't done any slides. He does it like this. Oh, that's it now. Yeah, that's the presentation, Robin. Yeah.
That's right.
Is that if this is no problem, you go on.
That's it now. We have it now here. So will you tell him when to start? Or no problem.
Okay.
Large.
8 minutes left. We have 8 minutes.
Yeah.
45.
Now. I can see that.
Yeah.
Can he see that?
So he
Check.
waits here. Does he have to do anything more? Except wait. Did he wait?
Yeah, we wait a few minutes so that anybody can come, not missing.
So will I share content? Is that it? Share. Will I do that one? Will I share video? Yeah.
Yeah.
Does that help? Oh my. You don't know. You don't have permission. So you can hear anyway. So Robin can talk.
Yes, we can hear. We can hear very.
So you will tell him when to start. Yeah.
Very clearly. Very clearly we can hear.
So you will tell him when to start talking. Will you tell
this file okay for you?
It is. We can see it. Yeah, we can see it.
Presentation. Open. Is there any other file you'd like to upload to computer and online?
You want anything else to upload, Robin? No, just the 4 pages.
No, there's
Just no problem. So we'll wait 5 or 6 minutes.
Can I move the? I'm trying to scroll through this. Hussein.
Let's do this.
What time in your country now?
In our country now, it is 25 to 9. 5 minutes more. 8:47. No,
here 25 to 11 here. 2 hours.
Yeah, 8:37. That's what you do. You don't know how to do this, do you?
3 minutes left.
If I can move it on that.
Now you will have to turn the pages for him.
No, I'm turning them.
Oh, can you? Okay, then.
If I can do it like this.
I couldn't get to the next page, but you can.
Hello?
Hello.
Can you hear me?
Yes, we can
You
hear.
see my image.
Probably not from Trinity College from Ireland will give his talk online.
Okay, are you with me?
It is 4 minutes to 3 minutes left. We better wait a bit.
Hocam bir mesaj gelmiş galiba şey. Laptop kendisi beraber. Eğitimde şey. Şey, doktora mı yapıyorsunuz? Nerede yapıyorsunuz? Kimde? Ha, hep şey, yüksek lisansta gerçi. Benim çalışıyorsun. Doktora onunla mı yapıyorsun? Yüksek işte o birisiyle daha çalışıyoruz. Şeyden Marmara'dan bir hoca var. Ben Bursa'daki yüksek lisanstan biliyor bunlar. Yani Bursa'daki o şey bayağı çalışmalar falan çok yani. Cemil zor ama haberin olsun. Ben yüksek lisansta yaptım.
Ama alışmıştım. Yani öyle başladık aslında. Yani ben mesela seçmenler falan hep dediler senin sorularından sonra. Onlar sayesinde böyle bir rahmetini duydum.
Hocaların çalıştığı şey.
Yes. And Professor Robin Hart Bilgi Wistrok, online from Ireland. Here you are.
Okay, can you hear me?
Yes, we can hear you very clearly.
Okay.
Çarpıya basıp şurayı kapatabilir misiniz? Ekran büyüsün biraz. En sağdaki çarpı hocam. Çarpı.
Ekranı şey yapalım. Şunu devre dışına tut. Sağ tarafı. Ha şuraya.
Is everybody ready?
Yes, we are ready. I think everybody is ready.
Okay, so if I start scrolling, will that help? Hello?
Hello, Professor Robin.
I'm speaking, I'm here. Are you ready to go?
I am Osman Mujuk. How are you?
Say it again.
I am Osman.
Oh, how are you? Good
Thank you very much.
morning.
Thank you.
You can hear.
Yeah, I can hear. Very nice.
Okay.
Nice to see. Nice to hear you.
Thank you very much.
Okay. Thank you very much for your talk.
So shall I start scrolling?
Yeah.
Are we ready?
Yes.
Have you got an image on the screen?
What's wrong now?
Been talking to Mr. Osman, and I'm asking him, have I got an image on the screen?
Is your paper started? No? Should be started now, or almost 10 minutes overdue.
Hello?
You saw the people there, did you? Hello?
No problem. Is there any problem?
Hocam başlayabilirsiniz.
Efendim?
Beraber başlayabilirsiniz de yüksek sesle söyler misiniz?
Duymuyor mu?
Biraz daha ağır sesle.
Robin,
Hello?
are you ready to start?
I'm ready to talk, yes, and I have
We are
an
ready
image of
for
you
your
got an
starting.
image on your screen.
We are waiting for you.
Okay, here we go. Okay, we're talking about something called a mixed identity. Did you get that? Hello?
Yeah. Yes. On the mixed identity for non-modules, you will
Now
talk on.
you're getting warm, so I'm ready to go. Are you ready to go?
Yes, we are ready to listen to you.
Okay. So I have to thank Mr. Dragan Georgievic for bringing me back to a very early stage in my professional life. And first of all, I want you to reflect on the Cartesian product of sets, which is not in my script. But the whole point about the Cartesian product of two sets is it's a procedure for converting functions of two variables into functions of one variable. And if your sets are linear spaces or abelian groups, then you want to convert bilinear mappings into linear mappings. So let us forget about it. So let us give ourselves two linear spaces or abelian groups, and we're going to call them capital N and capital M. And then we're going to build something called the tensor product of capital N and capital N. And everybody has heard about these tensor products. And the tensor product, so now your N and your M, they're abelian groups or even linear spaces over a ring. And when you stick them together in this way, you get an abelian group. And hello?
Hello.
Now
Excuse me, please. Could you extend the screen a bit large?
are we here?
We cannot see the screen. Just is it possible to extend more?
I have a small image of the presenter.
Yeah, you can also do what I do. I think I make screen down a bit.
Hocam siz yapabiliyorsanız siz yapın oradan biraz.
I made screen down. Robin, can you hear me? Where you?
I can hear you.
Is it okay,
I
please?
can now hear an image of your lecture room, but my wait now.
Can you hear? All okay? Tamam.
My script is obscured by the moderator.
Oh my.
What's it there somewhere? There we are. That's it.
Is it okay?
Hossein, can you hear him?
Is it okay now?
Yeah, it's okay. Can he just continue talking?
Yeah, I do.
If you can see the screen, I'm happy. So the whole point is that if you go into abstract groups, abelian groups, which are moduled over a ring. And if you forget about the ring and just have the integers, you're only looking at abelian groups. And then what you do is this is a group analog of the Cartesian product, which converts functions of two variables into functions of one variable. And if you start with bilinear mappings, then your Are you still with me? Okay. So the whole story is that linear mappings from the tensor product into another group or the module mappings from one factor of the product into the mappings from the other factor. Are you there? Are you still getting it? And you can do this with two rings, as you've got a sort of bi-module structure. And if you make one of those rings just the integers, you're down to modules and tensor products. Are you with me? Hello?
Tamam, biz buradan büyütüyoruz.
So what I'm saying to do here.
Is the system okay?
What we're looking at, on the left-hand side of the equation, we have the linear mappings from the tensor product into another linear space. Are you ready? Are you with me?
Yes, we are with you.
Have you got a better image of my page than I have?
This page is all right with you.
Can you see the page?
Yeah, you can see the page. Are you on this page? You are not reading. You are talking differently from the text.
Yeah, I'm addressing the text, and we've kicked off with it's a little bit like a Cartesian product, but it's more subtle than that.
When you go down on the text on the screen, please tell me if you can see the text on the screen.
We can see the text on the screen, yeah?
Is it okay now, screen, for you?
Can you see it? Can you see it?
Yes, we can see, we can hear.
Well, Robin has it as well.
Yeah.
Okay.
No, we're happy out.
Yeah, we are listening to you. We are
You
ready.
can hear me. So
we can hear you.
We're starting out with that. We're starting out with an abstract linear or stroke additive result from the theory of ring modules. And then the tensor product is a device for converting bilinear mappings into linear mappings. And here the word linear extends to either additive mappings on abelian groups or linear mappings or real or complex vector spaces. And the mixed identity says that the linear mappings on the tensor product reduce to the module mappings from one factor into the module mappings on the other. And that's the mixed identity. And it's just like saying that when you take the image of a pair of elements M and N, you so that's a purely abstract linear result. And then what I did a long time ago, and it seemed very pointless at the time, was to replace those linear spaces with Banach spaces, normed linear spaces over the reals or the complexes. And then when you confront the tensor product, you have to give that a norm, and there's something known as the greatest cross norm. And when you do that, you have another norm space. So we take this abstract module result about module mappings on abelian groups, and we convert it into a result about bounded linear mappings on Banach spaces. So what we're looking at, if you're still with me, what we're looking at is that the bounded linear mappings from the greatest cross norm tensor product into another Banach space are the bounded linear mappings. We're now looking at the module mappings from one left module to another respect the ring elements or the algebra elements as the new scalars. So capital T of A times M is A times capital T of M. So now we're looking at a bounded Banach space analog of an old purely algebraic thing. Is what's known as the mixed identity, but it's a result of Banach spaces. And this was a foolish project which it wanted to take the corpus of linear functional analysis over normed spaces, real or complex, and we wanted to stick a complex Banach algebra in where the scalars used to be. So if you wanted to embark on such a project, then you would want to do duality theory. So the module analog of duality theory for normed left modules, you would think would be the so-called dual space. You would think would be the bounded module mappings from your left module into your scalar algebra, the algebra of scalars. And people tried that. There was a Leopoldo Nachbin from Brazil, and there were Bonsall and Goldie from Newcastle in England who flirted with this duality. And the history of their papers was that the Banach algebra needed to satisfy special conditions. In their words, it had to, quote unquote, represent its own linear functions. And that project didn't get very far. So we had this idea in our head. You look at the dual of a Banach space. That's the real or the complex linear mappings into the real or the complex numbers. And if you look at this mixed identity from the tensor product and tensor M into another Banach space, capital P, then it tells you the dual space of N tensor M is the module mappings from M into the dual space of N. And when you specialize that capital N, this other factor in the tensor product, if that is your scalar, your Banach algebra that you're working with, then what you get is the the old Banach space dual of a non-module M coincides with the bounded module mappings from M into the dual of the Banach algebra capital A. So the new idea for duality of known modules was to send the module elements into the dual of the coefficient algebra. And what that meant was that the newfangled module dual was just the old scalar dual. So the old dual that we had before ever we invented this newfangled module structure was the same thing. But of course, the new thing now had this extra module structure. So the module dual of a non-linear module M is the bounded module mappings into the dual space of capital A. And that's a result which addresses an old problem, because the Hahn-Banach theorem and the duality theory for real known spaces was developed several years ahead of the corresponding theory for complex spaces. And so this modular result encapsulates this very old, what we needed to know was that the real dual of a complex space was the same as the complex dual. So here, this module result is a kind of inflated analog of an old result about real and complex known spaces. Now, of course, that means that you're working with the old dual, and when you're looking at the real or the complex numbers, the real and the complex dual, the real dual of the complex numbers is just the complex numbers again. So our foolish exercise in module duality has recaptured the old vector space duality. Now there's a little bit of spin-off apart from recapturing this old result, is something called the double commutant theorem, the von Neumann double commutant theorem for C-star algebras on Hilbert spaces. And there are two characterizations of a von Neumann algebra, one of which is that the algebra is its own double commutant, and the other one is that C-star algebra on the Hilbert space is a dual space. So the von Neumann double commutant theorem says that those two things coincide. And and this mixed identity can give you one half of that identification. Because if you extend from your Hilbert space capital X to a reflexive Banach space, then what you do is you take, if your capital A is the commutant of another algebra B, then you can tensor the dual. Now we have X star tensor X, where X is your reflexive Banach space. And what falls out in the wash is that the dual, the Banach space dual of that tensor product coincides with the module mappings from the space into itself over the new algebra B, which coincides with capital A. So your capital A, if it's a commutant, turns out to be a dual space. And that's one half of the Farm-Neumann double commutant theory. Now, there was another curious result due to somebody called Richard Ahrens, and Richard Ahrens had an obscure, he had a result about bilinear mappings between norm spaces. And then he discussed the second dual of that bilinear mapping. And the essence of that, the essence of that was that the second dual of a Banach algebra was another Banach algebra. So the famous Ahrens result says for a Banach algebra A that capital A double star is isomorphic to, this is the mixed identity in action again, so the bounded A module maps from A star to itself are the same as the scalar dual of A star, which is A double star. So when you inspect that isomorphism, you observe that the A double star is isomorphic to an algebra of operators, and therefore it's another algebra. And the Ahrens multiplication is an added complication that there are two Ahrens multiplications on a dual of a Banach. And one of them is displayed by treating that dual space as a left module, and the other one is obtained by treating it as a right module. So this mixed identity for normed modules is giving us back the phenomenon of the Ahrens multiplication. So then we wonder if there is any, we then look at an old friend, something known as the integration spaces. So when you have a measure space capital omega, then you have a whole bunch of integration space capital L sub p of omega. And these spaces have almost everywhere pointwise multiplication. And with respect to almost everywhere pointwise multiplication, these guys are normed modules over the corresponding space capital L infinity. So capital L infinity of a measure space is a commutative Banach algebra. It's bigger than the continuous functions, and it's a very nice Banach algebra. And we can now look at the tensor product of two LP spaces, the LP tensor LQ. And if you fiddle around a bit, you discover that that tensor product agrees with the pointwise product. And the pointwise product of LP and LQ is equal to L capital R. And by Holder's inequality, you find that 1 over P plus 1 over Q is equal to 1 over R. And now if you feed in this, if you feed this data into the mixed identity, you find for a start, the L infinity algebra is maximal abelian on each of the LPs. And then you get related results for the multiplication between LP and LQ. So the mixed identity is telling you that the capital L infinity algebra acts in a maximum abelian fashion on the LP spaces. Now, if you specialize that to a a discrete, if you go down to counting measure on a set omega, then you might use little LP to describe capital LP. So obviously that result about module structure for the capital LP spaces persists for the little LP spaces. And now you can look at a vector valued version of that. You can look at the famous Schatten ideals on a Hilbert space. So there's a culture of algebras of operators on a Hilbert space, ideals of operators on a Hilbert space. And you have a sort of little L1, capital L1 on a Hilbert space capital X would be the trace class operators or the nuclear operators, and little L2, capital L sub 2 on a Hilbert space X would be the Hilbert-Schmidt operator. So now the algebra of bounded operators on your Hilbert space is the coefficient algebra, and now you plug in the mixed identity and take your tensor product over again, and you get a tensor product structure for these Schatten ideals, which mirrors the pointwise multiplication of LP of measurable functions on a measure space. So there is the mixed identity, and then then you can go to a locally compact abelian group where you have HARTE measure. And now instead of capital L infinity, you would be looking at the capital L1, the L1 of an abelian group. And there's a problem there because capital L1 does not in general have a proper identity. It is only an approximate identity. And that makes, so what you do there is you take the multiplier algebra, capital M of G, that is the measure algebra, the multiplier algebra of L1 of G, and now you have module structure again, and the module product of LP and LQ now is isomorphic to the convolution product. And relative to convolution multiplication on locally compact abelian group, you have an alternative outcome. So now LP of G, convolution LQ of G, is a different capital L little r of G, because now you have 1 over P plus 1 over Q equal to 1 plus 1 over R. And one of the reasons when I was fiddling with this years ago, one of the things which stopped me in my tracks was the very nice paper of Mark Rieffel. And Mark Rieffel in 1967 produced a very lovely paper called Induced Banach Representations of Banach Algebras and Locally Compact Groups in the very first edition of the Journal of Functional Analysis. And here he was doing all this tensor product stuff without even a proper identity. And I became so shocked by this that back in those days stopped me in my tracks. So this paper, which Reagan Georgievic has dredged out of my early history, is an attempt to kind of pick up at the point where I left off in the early 60s. Now I will send Hussein, I will send Hussein a revised copy of my notes for this, which he will he can circulate that to anybody who is remotely interested. And I have kind of polished this up a little bit. And I would like to thank you in Maltapay for your attention. And thank you very much.
Thank you, Professor Robin Hart. Is there any questions or comments to
Thanks.
Thank you very much, Robin.
Thank you, Hussein.
When you go to summer holiday to Kuşadası in September. Neyse. Thank you. Kaydı durduruyorum.